So welcome to the R by 3B series. In this episode, we'll try to bring up the UART on bare metal. Okay, so I will start from scratch. I will go through which all folders files I have to create, and live we will write the code and try to build the kernel image, and then we'll load that kernel image into the RPy and see the output. So let's start. Let me first create one folder, some folder first. Okay, so uh, create one folder src, then not inside src, another folder inside play with bits include folder. Okay, so inside src I will add some files like let me add first I will add that bootuf file. Okay, so that file I will give boot.s file name. Okay, let's start here, start coding here. So actually before that we have to create some header files to store some of the base address of that UART peripheral and GPIO peripherals. So that I will create inside include. I'll create one folder. Let me create a peripherals folder. Okay, inside peripherals we will create base.h and one for GPIO, and then we'll create one auxiliary file. Okay, now let's start with base.h. So inside this basically we have to create store the base address for the peripherals. Okay, so just I will define the pragma just to include this file only once. Okay, and our peripherals base will be 0x3f1234. Okay, so this will be our peripherals base address. Okay, and then we'll define inside GPIO which all will define some of the structures inside the GPIO, and we have already gone through the GPIO register space in the previous video where I have shown how the register space is organized. Okay, so here I will directly go through the definition of that structure. Using that structure we will directly do read write to the registers which is available in the GPIO space. Okay, so let me include ones, and then we will include peripherals, and then let me define struct GPIO pin data. It's suggesting, but whatever it is suggesting, that is not correct, and I think I should disable this. Okay, so it is suggesting correct but not exactly, so let me do it by myself. Some utils function also I will define. Okay, this reserved we don't need 2 bits of reserved, we need only one, and then as 32 data. Okay, so let me first define this reg32, and this reg32, how this reg32 is defined, that we will do once, and after that we will see. So I will define for this one, I will create a separate .s file inside src. Let me create one file utils.s. Basically here I will be defining some of the functions like to read and write 32-bit register. Okay, so I'm defining the global. Okay, just to write 32-bit. Okay, I will store that into x0 and then return. Okay, similar way I will define get 32 to get the value of a register. Get 32, I have to load that w0, I have to read from that x0 register and then return. Okay, so this will be our two utils functions. which will help us in directly reading and writing the 32-bit register. Okay, let me include this file. Let me create a header for this and include this inside our G, uh, include this inside our GPIO.h. Okay, because this is what we are going to use to read it. Okay, so one more thing I will define. I will define one more folder inside this include. Inside this include, I will define one more file, not folder. I think file will be better. I don't want to define inside directories. I want to define inside include. Okay, so where it is coming. Oh, let me first do it and then I will move it. Common.h. Okay, it's outside. Okay, here also I have to define pragma once and then include standard integer std int.h, and then I will give the type def for each of this register, the utils function which I have written in the utils.cs. Okay, type def volatile, then even 32 I am giving. Okay, this is fine. Type def volatile. Another is type def volatile event 16 for 16, and then I will give for event this is for register 18 16 18, and I will define one for 32. Type def volatile. Okay, 64, sorry, 64. So all this registers I have defined, and so this should be okay for instead of using the uint 8 and every time, I will directly use this res32, res16 and res8 to do read write to 16-bit or 32-bit registers. Okay, so now let's go to the GPIO file again, and there I will use this res32, res64 and all. Okay, so let's go to GPIO-H. So I'm already using it. Now let me define the structure. Okay, inside this structure I will define the GPIO registers. Okay, so GPIO registers, this is fine. No, okay, this is fine. Then we have function set, then we have out again reserved, then we have for clear 2 bits. This is also fine, and but instead of directly using this 32, this GPIO pin that I have defined, so we don't need to use this set of this. Instead here we will directly use like this function cell. Let me remove this and let me write this struct GPIO pin data, and the first one will be output set. Okay, so this I am writing based on let me show you uh, the data sheet again. Okay, so here we'll go to the GPIO part. I think in last video I have discussed this, okay, how this register space is organized, and based on that only we are doing what happened. Where is that GPIO? Okay, GPIO is page number 89 and 6. Okay, GPIO here. So here what we are trying to do, we are trying to put a structure using which we should be able to do read write to all this register space. So as you have seen, I have declared a function select of array of 6 32-bit integer with 6 size array to actually access this GPIOs, and after that I am writing it for setting the output. This is I am clearing for the this I am reserving 132-bit for the reserve, then setting the GPIO output, then clearing again reserve, then clearing the GPIO output. Okay, so this is how I will define my structure now. Okay, so let's go back to the code. Okay, so this one is function select, then I will define for output select, where the first bit will be reserved and the second bit will be the data. And after this we have struct again, then GPIO pin data, and then output clear correct, and then struct again GPIO pin data, then pin level would be there correct, and then struct GPIO pin data, then event detect status will be there correct, and after that we will have rising edge detect. As you can see, I am following exactly this thing. So here you can see after output we have pin level, then we have detect status, then we have rising edge, then we have falling edge, and pin high detect, low detect, async rising, async falling, and then pull up enable, and pull up pull down enable, and pull up pull down clock. Okay, the same way I will follow there also. Okay, so even detect status is done, and then we'll go through the rising edge, then falling edge, then high detect enable, then low detect enable, then async rising edge. Actually, this AI has detected that register space and directly it is suggesting from there. But you should keep verifying whether it is giving the correct one or not. Okay. So now async falling rising edge, async falling edge detect enable, and then we need some 32-bit reserved space. Okay. Okay, reserved, and then we need that's 32 again. Pull up, pull down, enable. We need pull up, pull down, enable. Okay, and then we need reg 32 for uh, enabling the clocks for pull up, pull down. Okay, pull up, pull down, and clock enable. That's it. So this completes our structure. Okay, rest of these things I will delete whatever it has suggested initially, and that is not correct. I don't want to go with that because I have already defined one structure to access the initial things. Okay, now I will define the GPIO base, and GPIO base, so this will be the peripheral base, and GPIO base is 2 lakhs. Okay, 2 lakhs from where I got this GPIO base. This also I had shown in the previous video, but I will show you here again where it is the peripherals base. So peripherals base, where it is defined. Okay, here also you can see 7E is the peripherals base address. On top of that, if you want to access GPIO, so 2 lakh, 20 lakh. So basically 20 lakh you have to add. So that's what I have added it there. Okay, you can see here, that's what I have added it here. But directly this is GPIO base. I want to give one GPIO name, reg GPIOs, to this register, to this base address of the GPIOs, and directly I cannot access. I have to convert it into the structure pointer of this pointer of this GPIO registers. Yeah, now it is suggesting correct. Okay, so this is using this directly I will access all the registers which are there inside this. Okay, uh, apart from this and this reg 32 definition, I have to get it from the uh, common.h, so that file also have to include it here. Okay, I should include the common.h. Okay, so I think this file we are done. Next we'll go to the, so basically gpio.h we have already defined. Now I will create a file in source gpio.c where I will write the function to first set the GPIO pin functionality and doing the GPIO pin enable. Okay, so let me create one file here, gpio.c. Okay, so inside this we have to create two functions basically. One is both these two function programming guide I have discussed in the GPIO setting slide, where I prepared slide, and there I have mentioned what all things we have to do for basically setting the functionality of a GPIO pin and then enabling that GPIO. Okay, so the function which we need is first, I don't want to return anything, so the function should be basically GPIO pin function set. Okay, set function. Okay, so inside this, here also it is giving the suggestion, but let me check it once. So here what is saying, say here it is passing pin and then function, and then we are taking that GPIO register. Okay, that went away. I think I have to first give tab and then we need to check. Let me type again GPIO function and then the GPIO pin. Okay, it came again. Let me do first tab and then I will verify. So that pin is coming as an integer. We don't need as an int. The maximum GPIO pins are 54 only. So we just need to use uint8 for the pin, and the function would be, oh, okay, function I have not defined, but function can be also maximum 6 alternative functions are there, right? So that also can come in uint8. Okay, next thing is I have to find the register index, and that register index would be uint32. Okay, so reg will be reg index, register basically you have to find, right? So let me define as an okay, so register also we have total like 6 registers. So there also, this is register index, this is not actually the register, this is register index. So the register index would be u8, and what we are trying to do, we are trying to uh, find the which index it will go. So from the base, right, as I have shown you before also. So here if I will show it again, so from the base basically we are trying to find out that GPIO pin will go in which of these 6 registers. So each of this registers have total is a can so this register 0 will be used to set the functionality of GPIO 0 to 9, this one from 10 to 19, like that way. So that's what we are trying to find out, register index. Okay, uh, so let's go there again. uh, so this pin number is fine, this reg index is fine, then bit offset is also. So uh, we need actually 3 bits. So here this is wrong, so this we should find pin number multiplied by 3, and then we have to do mod load 10. This we are trying to find the bit offset. Okay, so this should be like modulo 30, like this we will find the bit offset, and then we'll read the current value of this function select. We don't want to disturb the uh, other values. Okay, that's why we are directly reading, and then we'll create a mask and then write it. Okay, I think I should write some comments there also. Okay, so this one is we are using to basically read the register values. Okay, and then we are trying to uh, first clear the 3 bits which is used for setting the functionality of that GPIO. Okay, and after that we are basically setting that according to the function. So this function also will define based on this function either 0 0 till 1 total 8 functionality I have defined, right? So based on that we are trying to set those 3 bits. Okay, set the new function, and after that we will write that value. Okay, we'll write that value with what happened. I want to use this only like this. Okay, so after that I want to set here, write back the modified value. Okay, so this value we have written to this register, so this function is complete. Okay, what we are trying to do here, based on the pin we try to find which register index we should touch, and then inside that register which bit, what is the start bit from where we'll write the 3 bits that we are finding. Then we are reading the that register value, and only clearing that only 3 bits. Okay, and after clearing that 3 bits we are updating that 3 bits according to the new function of that GPIO, and then writing it back. So basically this function is completed for setting the function of a GPIO. Okay, next we have to write a function to basically enable the GPIO pin. So GPIO pin enable. Okay, I'll give that function name, and then we have to pass pin number. Okay, so pin I have passed, so let me first do tab, then we'll see the code. So here I'm taking the register index, and what it is trying to output. No, I have not defined anything like this. Okay, so it is not taking the correct one. Let me write it from starting. Okay, so let me tell you how we can enable the GPIO pin. So for that I think it has been given here how to enable that GPIO pin. If you go down, total 6 steps are there. You have to enable the PU, that pull up pull down register, and then you have to give the clock, and after some delay. Okay, so that's what I'm trying to find out where it is given. Here. So GPIO pull up pull down clock registers. So these are the steps basically to enable a GPIO. Okay, so the same thing, and I will try to do in the code. Let's go to the code, and here let me write. So first we'll write that GPIO PUPD enable as 0. First because we don't want to use the pull up or pull down. Okay, after that we need to give a delay of 150 clocks, 150 system clocks. This delay we have not defined, I think. Yeah, so we have to define this delay. After that we have to again basically write the pull up pull down clock enables. Okay, so clock the control signal into GPIO pins. Okay, GPIO pins. So it's GPIOs, then PUPD enable clock, and then pin is fine. Okay, so we have 2 registers. Basically each registers will give clock enable for 32 of the GPIOs, and the other register will give from 32 to 53. So if the index starting from that 0, so that PUPD clock enable, this is fine. Pin, then 32, then 1 shifted by that pin number. Okay, yeah, this is fine. And then we have to delay again. for 150 system clocks. Then we have to basically write to PUPD enable again to remove the clock signal. Okay, so that's GPIOs. Okay, commit. Okay, first write the code, write GPIOs, then PUPD enable, we have to write 0 to remove the clock signal, that is correct. Then again write GPIO, we have to write remove the clock. So basically here we have to remove the clock again, removing the clock. Okay, so now this function will basically enable that GPIO pin. So we have successfully added these two functions, setting the functionality and setting the GPIO pin enable. Okay, now we have to define this delay function. Let's define this delay function. Okay, so this function we'll try to define in utils.s. Okay, so here let me define dot global delay. So basically whatever value that will pass, one by one will subtract one from that value, and keep checking if it becomes 0 or not. If it has become 0, then we'll return. If it has not become 0, again we'll jump to the delay function. Okay, so basically we'll subtract by 1, and then if it is not equal to 0, then we'll jump to delay again, otherwise return. Otherwise return. Correct. So this delay function will use there. Okay, now let's go to the GPIOC. So here I think I have already not added. We have to add that headers for this utils function. Okay, so let's add that header for that utils function. I think before that we have to define that header also, but let me add GPIO.h because I'm using that GPIO reg GPIOs, so that one I have to include. And am I using U8 and all? I think that I have already added in GPIO.h. Common I have already added here, and then we have to create one utils.h utils.h that we have to use. Let me create utils.h. So whatever utility functions we have created, that we have to define here. Okay, hash pragma once, and then we have to define that here. So let's define that here. So basically we have to we have to include first we have to include common, because there we have some un that register macros, so reading and writing to that register that we have defined in common.h. Now let's define the functions which we have defined in the utils.h. So void delay, so this is coming not count, we'll give it as a u64 u64 then 6. Okay, and other function we have defined is to read and write the 32-bit. So put 32, we have given the 64-bit address and then 32-bit value. Okay, and then we have to define the get function also, use 32 get address. Yes, so this is also correct. Okay, so this completes our utils.h. This utils.h I have to include inside GPIO. So as include utils. Okay, utils also to showing, but I didn't. So utils.h. Okay, so this completes our functions for setting the GPIOs. Okay, so until now I have not written the boot test code. So here we have to write at least the code for the core 0, so that it can jump to the function main. And here I will define one main file also, main function. Okay, main.c will define, where I will write the c main function. So this basically boot code should initialize that core 0 CPU, and then it should jump to the main. That code also will write. Okay, so let's write this bootest.code first, and then we'll go to some other code. Okay, let me write the bootest code. Okay, so let's write hash include. Before that I think we have to do some we have to define the linker file, and then okay, I'll define that linker file later, but let's start. So we have to define this section here first. This section will be put inside the boot section. Okay, text.boot. Okay, this section I will specify in the linker file. Okay, then we'll define the start. So this is where the CPU jumps when I will give this address. This will be the start address for the CPU. Okay, and this address this is the address where I will jump from the U-boot that I will show. Okay, so let's first start global start, and then the start we have to write. So basically we have some affinity register inside the CPU, which will basically help us in finding the which core is basically executing core ID. Okay, so that register is that affinity register we call is that mpidr el1. Okay, so in this register, actually in this registers the lower 8 bit shows the affinity uh, shows affinity 0 value. Okay, affinity 0 bits. Okay, lower 8 bit. That's why we have to do mask with and mask with 0xff to find out the lower affinity value. Okay, so we have saved in the x0, so x0 will be masked with value 0xff. Okay, and then we'll compare this. If it has 0, then we'll jump to the another function which will give some name like master, and the rest of the course I want to keep looping inside a while loop. Okay, that those basically those other codes will be waiting for the interrupt. WFE we call wait for event or wait for interrupt. Either you can put inside wait for event or wait for interrupt, anything is fine. Okay, so now we'll define the master tag. So core 0 will jump to this master, and first we have to disable the uh, MMU here. Okay, so to disable the MMU we have a register, that is a system control register. That one we have to set. So that system control register we have to set. So what value you have to set, that we have to take it from we have to define one system reg.h. From there we'll take that value. Okay, so let me first define that system reg.h. That system reg.h I have to include add here system system, or we'll define it as sys reg.h. Okay, so let's define that sysreg.h. Here we have to define some things. We'll basically we have to define the bits which are used to basically enable or disable some of the features in the EL2 and EL3. Okay, so let me do the pragma ones. Okay, this disabling which basically this information to find out which bits I have to disable for MMU, which bits I have to disable for the cache, which bits I have to disable for the non-secure and secure. All this information you will get inside this. Okay, so there is a V8 ARM architecture inside this uh, ARM V8 architecture document. If you open architecture reference manual, so there you can find out all this register to basically okay, I will keep showing you here also. Okay, so that you should be able to understand. So each bit information you will get it here if you search that register. Okay, so let's go here first. So first we'll try to define the values which we are going to set inside the system control register. Okay, so let me define the macros. There are some reserved bits in the system control register, sctlr. Okay, reserved. Okay, this suggestion is sometimes create a problem. I don't want to take this. I want to just give tab, and this things you will get in that. Okay, so let me write some of this, because this I have find out from that document only. Okay, so other thing is 30, 22 bit, 20, and then 11 bit. Okay, these are the reserved bits. Okay, now we have to define inside that same system control registers. So we have to define that little Indian flag sctlr underscore Indian, and this will be 25 correct. Then we'll have hash define SCTLR. So basically we have to define whether we want to operate in Little Indian, Big Indian. So these flags are basically used for that. Okay, the detailed information you will get in that document. EOE. Okay, EOE, sorry, EOE, and then underscore Little Indian, that you have to build set 24, and then we have iCache. We have to set the iCache enable as at bit 12, and then dcache is at bit 2, and then we have MMU enable as bit 0, and then we have MMU enable and disable. Okay, so we have MMU enable at bit 0. Okay, so the let me define the MMU disabled bit now. I will use all this macros and combine it to create our value, which I should write in the system control register. Okay, so hash define, as define, we have to define system CTLR, system control register value with MMU disabled. Okay, with MMU disabled we have to define that result space. We don't want to enable the MMU currently, because if you want to enable you have to set up the page table and all. So I will go with MMU disabled, reserved, then Little Indian, then this disabled Little Indian, then we have to disable the cache enable and this one. Okay, so disable we have to do, we don't have to enable it. Okay, so this one is setting it, and we want to disable here. Let me write this one is basically for MMU disable only. We are setting the value to no, this one is for enable, and we have to define one macro for disable. SCTLR underscore MMU disabled. Okay, so this MMU disabled value, it is adding extra MMU disabled for that. The macro is yes, so this one I have to do. So here our macro should be STL reserved, then Little Indian, then we don't need this. Okay, then we need iCache disabled, we need unshifted by. Okay, here I need iCache also, I want to be disabled. Dcache also I want it to be disabled. Okay, here also I want to set it to 0, here also I want to set it to 0. Okay, so I want this one to be disabled, the other one also I want it to be disabled, iCache dcache disabled. So, and I want MMU to be also disabled, CRCTL disabled. Yes, so all these 5 things, I Little Indian, then iCache disable, dcache disable, then MMU disable. Okay, so this value we are going to write to the system control register. Okay, now we have to define some value for the hypervisor control register HCR. Okay, that also will define. Before that, let me show you the SCRCTL register. If you see SCRCTL, let me see. Okay, it's not SCRCTL, then that value is actually SCRCTL, it's SCTLR. It's SCTLR. Okay, so it's let me search again. That register says SCTLR. Yeah, so that is system control register. So this is for FAT A. No, this one we don't need, we need for A profiles. So each bit information whatever I have added there, you can find it here. So let me show you some of them. So this is for MMU, that bit 0, whether we want to disable or enable the MMU, and then we have some for this is non-secure and secure implementation. Okay, but this is for 32-bit. We can have 64-bit registers also. So this one is for exceptions after reset. So basically this document you can go through to understand each bit. Okay, let's go to our code now. Okay, so here we'll define the next register is a hypervisor configuration register. So there also will create one mask. Okay, inside that mask, let me first create that mask, and then we'll discuss one by one each of them. Okay, so let's define the hypervisor control values. Define HCR. This is some read write to enable the read write. Okay, set the enable architecture 64 for EL2 and further exceptions levels like lower exceptions level like EL1 and EL0. Okay, then we'll define the HCR value as HCR Okay, after this we have some other registers also like system control registers that also we will define here. Okay, so let me define first then. So basically whatever register I am going to set in this boot.s code, all this register information you can easily search in that v8 ARM architecture document. There you will get every bit information. This bit is used for what and what should be the value. So based on your requirement you can set those values. I am setting these values so that it works in 64-bit mode. All at EL1 or EL0, all it works in 64-bit mode. For that one only I am setting all these registers. Okay, so let's set this reserved. Then what we have to do? This one SCR. Here we have to define the secure and non-secure. Okay, so define SCR RW first. That is bit number 10, setting the architecture to for lower as a 64-bit, and then we have to set to non-secure world. Okay, we are going to enable the non-secure world in EL1, and then SCR value will create the mask from all this. Okay, now after this we have to select the there is a program status register, that SPSR. Okay, so that will help us in creating the masking all the other exception levels. Okay, SPSR mask all, we want to mask all the exceptions. So for that this macro I'm creating. Then if at exception level 1 through handler context, so at every exception we have either two contexts, one is handler context and one is thread context. So for handler context we have to set this bit as that fifth bit as 0. Okay, and for EL, now after this we have to set that this same status program register, right? That also have to set at EL2 handler. That also have to mask as define SPSR, then EL2H. So this one also we have to mask EL2 execution state using this status program register, and then SPSR value we'll create from this mask SPSR value. Okay, this value will create SPSR mask called then EL1H. Okay, so this completes our system reg definition. Now we'll go to boot.s, and there we'll define now there we'll write the code to basically jump all this code from this boot.s to main. So that is our main purpose. So here I'm disabling. So to disable, basically I am loading this value inside this x0 register. This sorry. Okay, so sctlr value mmu disabled. Okay, then I will actually one more thing, this MSR register we have to do read or to write to any of the system register. That's why we cannot directly use we cannot directly load value to the system register. We have to use, they have given a special opcode MSR to load the value inside the system register. So we load inside sctlr underscore EL1, we'll load this value x0. Okay, so this completes this will disable the MMU. Then we'll do hypervisor, we'll configure hypervisor register, hypervisor configuration register. Okay, so here I think I have already told, this is to basically tell the execution states of the EL2 and the lower exception levels. For that we are setting this value. We have to load first that value inside the x0. Okay, XCR value it will load, and then we'll write to the secure configuration register. This we have to again use MSR, then SCREL3 exception level 3 registers. So this the suffix tools tells us this register will be accessible at which exception level. See, I'm trying to access EL3 register, so definitely this should be running at EL3. Okay, so I think I have given one startup code walkthrough in one of my video, where I have told key if you will not replace the default ARM stub, then this boottest.code will start executing from the EL2. Okay, and in EL2, if you try to access any register in EL3, then basically that system will create an exception. Basically, you're trying to access a register at higher exception level from the lower exception level. That's why we need to write the ARM stub also, so that the start will start executing at exception level 3 instead of exception level 2. Okay, so that also will do. Let's first complete this one. MSR we have written to this one hypervisor. After this we will write to that SPSR. So let's load x0. Similar way we have to do here also. We have to load that value inside the x0 register, SPSR value. Okay, then we have to save. So this SPSR we call it as a saved program status register. Saved program status register. Okay, so this one actually holds the processor state whenever you are giving an exception, whenever you are taking an exception at EL3. Okay, so this is basically used to save the program processor state. Okay, so MSR SPSR EL3. This one is also at EL exception level 3. Okay, so we are basically writing this value inside this SPSR, and basically this is about saving it in the processor state. So that processor state we have created a mask here, then we are saving it here. Okay, after that SPSR, now we have to basically give the address to jump from EL3 to EL1. So first I will load the address of EL1 entry. Okay, and then I will write this address inside that EL3 exception link register. So, and after that I will do ERET, so that we will jump to EL1 exception level. Okay, EL3 x0. Okay, then I will give ERET to return from this exception level. Okay, so now this completes the changing of exception level from EL3 to EL1. Now we have to go inside EL1 and write some of the functionality that I will tell what all things we have to do at EL1. So EL1 entry, we have to basically load the BSS, initialize the BSS with 0, initialize the stack pointer, and then jump to the main function. These 4 functions we have to do inside the EL1. Okay, so let's load the BSS section. So I will load into x0. So this BSS begin tag we have to define in the LDR. Okay, in the linker, in the LD file. That also I will show you. BSS begin, and then we have to load inside x1 the BSS end section. Okay, so BSS is the section where all the uninitialized data section will go in the BSS. Okay, initialized data section goes inside the data. There is a data section memory, code section memory. There is a BSS section. So all uninitialized global variable will go inside the BSS, and that will be initialized to 0. Okay, so BSS end. Okay, then after that we will find the size of this BSS by subtracting x1 from x0. Okay, x1 will save the result in the x1. Okay, and then we will jump to one function where it will zero out all the BSS section. That function also we need to write in one of the functions, either utils.s or somewhere we have to write that. Okay, we'll write that. Before that, let me set up the stack pointer at EL1. So this macro also we need to define. So stack grows from given location to the upwards, right? That's why we have to give the stack pointer. From here the stack will start. Okay, so this low memory also will define, and after initializing the stack pointer we will jump to the main function. That main function I will give kernel main as a name, and others can go to the branch to the if other code have come here, then we want to branch it to the proc hang. So let's define proc hang tag also. So proc hang basically will keep waiting for event WFE, and if it is not there, then again jump to proc hang. Okay, so basically this completed our boot.s. So now after this we'll write the what I call linker, but before that we have to define some of the macros like low memory and all. For that I can define inside this sysreg.h. Okay, let's define in sysreg.h. Okay, so that low memory pointer I will create one new file inside include, and that I will directly copy that code. I will tell you, I will not type it, I will directly copy and then paste it. So let's go to the create one file inside include. Inside include we have to what happened inside include I want to create one file mm.h. Okay, and I will paste the contents here. This is already written. So basically this mem0 function will zero out, and we are giving source the start address and the size to zero out, and this low memory is basically where we are initializing our stack pointer. Okay, so all this page shift ph table and shift section I will talk about when I will go through the MMU section. So in this session I am not discussing about the MMU. We have disabled the MMU, and that's why I will talk about all this low memory on and all inside the MMU, separate video on MMU. Okay, for now we have defined it like this, and the same thing we are going to use in bootest. So but here we have to include that header. Okay, so that header will include it. Let me include that header in boot.s. So hash, why is not working, hash include, and then we'll include that header mm.h. Okay, and the other header we have to include it sysreg hash include, then we have to include a sysreg.h. Okay, so these two we have included. Now we have to write the linker and then make file. If we should be able to write the linker and make file, then using these two we can build our this code, this binary, and then we can execute. So let me create a make file, and that make file will create in the top level. Okay, so no, I don't want to include inside src, and I have to create in the top level. Okay, let's create. I will move it from the make file. Okay, this make file I want to move from here to make file to just move it. Okay, and this make file, instead of going through each of them one by one, I think this make file I will take directly from my existing code, because that make file you can understand based on that also I will explain, but in a separate video. Here I will try to build and show you that what is working or not. Okay, make file I will copy and directly I will paste it here. Wait, make file I will paste it here. Okay, we have to modify some of the build directories and all that. I will change it. Okay, but one more thing I want to do, I have to define the main function. That main function which I have written here, that kernel main I have not defined. So that will be basically for jumping from here to here, and inside that main function I have not defined the UART. Okay, so this here I have just defined the GPIO. I have explained the bootest code for basically jumping from EL3 to EL1, and which all system register we have to configure. That one I have defined, and I have defined some of the structures for accessing the GPIOs. Okay, inside GPIO.h inside this file, and I have also defined how I have defined all this from the datasheet. Okay, I have defined some of the functions inside utils.s, that we have defined a delay function, we have defined a function to read and then write to a location. Okay, so these things we have defined, and still to show the working UART, there are a lot of other things I have to do. So I'm thinking to stop this video here and record the next video from here, where I will put the main function. I have to write the UART driver. I have to tell about how to write the UART drivers. I have to explain about the UART hardware, UART registers and all, basically, because this will just help in setting up the function and the enable. So, but we need this, otherwise we will not be able to configure the GPIOs which I am going to use for UART. Okay, so at least I have given some stage one level to basically build the bare metal for the R by 3B. On top of this, next we'll try to write the main function, we'll try to write the UART drivers, and we'll try to build those binary and load inside our RPy, and then we'll see the output. Okay, all those things I will do in the next video. So I will say please subscribe to this channel so that I will also get some motivation to do this. Okay, and this will basically, if you write the code and basically execute it on the real hardware, that will give you a completely different feeling. Okay, that will give you that the confidence that it will give you, that you can never have if you just write it code and just build it and it doesn't work. Okay, that's why I have tried to explain each and every register inside this booters, how to write the GPIO bare metal functions to basically set and set and enable the pins, and also how to write the structures basically directly from the data sheet. Okay, so basically writing these things actually will help us in directly doing the read write to this registers. Okay, and I have also defined showed the peripherals base address, and okay, and inside auxiliary.h I have not defined this. I have created to define the base address for the mini-uart, which is available in the RPy3b. Total 3 auxiliaries are available, so those base address I will define it here. Okay, and makefile, by the time you can go through the makefile, this all code I will put in one of the GitHub, and that GitHub link also I will share. Maybe I will not share immediately, I will share in some time. Okay, so these all things I have tried to explain. Please subscribe so that it will give me also a motivation to basically proceed further. Yeah, thank you.